So thanks, Mark, for hosting this and inviting me. Really happy to present. Okay, I just set this up a bit. All right, so I'll get started right away. All right, so today I'm going to be talking about this QuNetSim project. And QuNetSim is part of the Unitary Fund grants. And for those not familiar with Unitary Fund, it's a funding agency kind of that provides us. It's kind of an organization that is funding small open source quantum software projects. So they provide micro grants, and QuNetSim was one of the projects that they funded. Okay, yeah, so to get started, I want to introduce what quantum networks are. So quantum networks are not much different than any other type of network. They're designed to connect different nodes that are not directly connected, but can be used to move data around through routing algorithms and things like this. So a quantum network, in principle, is a collection of nodes where these nodes want to transmit, in this case, quantum information or quantum states between themselves. So for example, if you have two nodes in a network, so let me know if these terminology is too confusing. I'll explain it further, but assume you have two nodes in a network like Alice and Bob, and they're not directly connected, but they're connected over a network. So in between them sit some more nodes that we would call like relaying nodes. And what Alice wants to do is send a qubit to Bob. So what what Alice does is she prepares her qubit, puts it in the quantum network. The quantum network will route this qubit somehow, and hopefully at the end of the day, Bob will receive the qubit that Alice sent. And in reality, this qubit could be decohered. I mean, it could have like the noise in this process will definitely apply to the qubit, and this network should accommodate for all these things. So moreover, a quantum network should also enable the ability to share entanglement between two distant nodes. So this property is maybe even more important than the first. What that means is any two nodes, there should be something that the quantum network does so that Alice and Bob can share entanglement even if they're not connected directly with a fiber. Okay, so that's what quantum network is to me. And so then what's QuNetSim? So QuNetSim is a Python network, a Python framework for developing simulations of quantum networks. So with these quantum networks, they're both classical and quantum connections. So this means that this network can do both classical transmission, so bits or strings like hello, and it could do quantum communication and quantum transmission. So it has both these classical connections and quantum connections. So what I picture is you can think of like a computer or something that has a processor for doing classical computing and a processor for doing quantum computing. And what QuNetSim does is it allows users to write simulations for this type of network, right? Okay, so more detail. Oh, I just hear some birds in the background or something. Okay, I'll talk over it. So QuNetSim, it allows the users to develop and test protocols for quantum networks. So some of these protocols, for example, are quantum key distribution, quantum money, which is a protocol for ensuring that money is unique and non-clonable and things like this, or anonymous transmission is a different type of protocol. There's many quantum networking protocols. There's actually a list of them on the internet one could search for. And another thing it's good at doing is it allows for eavesdropping to be implemented in these quantum protocols. So a lot of the time you hear things are perfectly secure. Quantum key distribution is a secure method of securing a communication line. And this is because the quantum properties of quantum key distribution, for example, when someone is listening in on the communication, the sender and receiver can detect this. So this eavesdropping property is kind of nice because you can test for security, for example. Another thing QuNetSim does is it provides a toolbox of common quantum networking tasks. So this allows the user to build on top of things that people already do really commonly. So for example, something that is really commonly done is teleporting quantum states between users. So we tried to, sorry, there's a bit of background noise again. yeah, we tried to, oops. Yeah, we tried to include all these protocols so that users can use them to build new protocols instead of reinventing the wheel every time they want to make a new example, so to say. And lastly, it uses multi-threading behind the scenes so that we can mimic this behavior that a network has where users transmit, or like nodes in the network are transmitting messages to each other, but there's this delay and waiting process. So I think this is an important feature that some other simulators are not doing because it's maybe too early in the game to be thinking about such things. But I think when you think about the applications of quantum networks, and this becomes more useful to be able to simulate. Okay, so there's three main components of QuNetSim. And these are, so the first one that I'll talk about is the host. And the host is kind of the application layer of the network, if you think about it like this. So the hosts are these nodes in the network. And these hosts have the ability to process and store quantum and classical data. So they can, for example, store qubits, they can store EPR pairs and other types of quantum information. They can either act as an end node, so running an application, or a relaying node. So these relaying nodes are the kind of the nodes in the middle. So in that picture from the beginning, I can just go back quickly. For example, these nodes over here would be considered the relaying nodes. They just act as nodes that are used for routing. And they can run any custom instructions. So I can program these hosts to do pretty much whatever I want. That's in the universe of QuNetSim. So the next part of QuNetSim is this transport layer. So the transport layer is kind of packetizing the information within QuNetSim. So when a host, for example, wants to transmit a qubit to another host, first it goes to, first the application runs this application, then it goes to the transport layer. Transport layer puts this kind of classical information on top of the quantum information, and then this packet will go into the network. So, and then one more feature of the transport layer is it checks that the host running the application has the necessary resources to run the protocol that they want. So for example, if the host wants to run teleportation requires that the two users have a pre-established EPR pair. So the transport layer can handle things like just generating that EPR pair ahead of time to simplify the process for the user. And then lastly is the network layer. So the network layer is performing the routing. And with the network layer, the users can program the network to route in any custom way. So standard way is usually like shortest path between two nodes, but you can program it to use a different method. For example, we have one example where we take the path that most entanglement has been established on ahead of time. So these kind of routing algorithms can be tested using QuNetSim. And we can use the network layer to draw packets or apply errors to qubits along the route. And lastly, it can simulate this multi-hop entanglement. So this entanglement swapping protocol, where entanglement swapping is a process used where, for example, Alice wants to share entanglement with Eve, but they're not directly connected. So first what she does is establish an EPR pair with Bob. Bob establishes an EPR pair with Eve. And then Bob performs a certain measurement such that at the end of the protocol, Alice and Eve are sharing the entanglement. So QuNetSim has that part kind of built in if users want to test such a thing. So this is really common this is necessary in reality when two hosts want to share an EPR pair not directly connected. So this is something that's going to have to be implemented in later stages of quantum network development. Okay, so how does QuNetSim work behind the scenes? It's mainly it's kind of just handling a bunch of threads and listening for behavior in the programs. So a host is kind of like a thread running idle, and it has this packet queue. So it's just kind of listening for packets to come into its queue. And once the packets arrive in the queue, then the host starts processing. And it's kind of just like a standard way of simulating such a thing, I think. And the network is also listening. So when I say something like the transport layer puts the packet into the network, what that means is the transport layer puts a packet into the network. Okay. Am I muted still? You can hear me?
Yeah, now we can hear you.
Oh,
yeah.
Oh, sorry. Okay. Yeah, so it's kind of just a bunch of threading and listening for things to change and then reacting to those kind of changes. And that's pretty much all of QuNetSim. And then there's the next part. So yeah, this little animation and well, animation, it's like, so the hosts are listening, packets coming in, no, no, no. And then finally, yes, and now event triggers and something happens in QuNetSim. And on top, underneath QuNetSim also is the ability to change the qubit simulation backend. So what we do is we kind of put on top of these pre-existing qubit simulations. For example, Project Q is widely used for doing quantum computing simulation, but it has a really good qubit simulation as well. So we use QuNetSim to control like Project Q, for example. We also support other backends, and we've kind of like wrapped these libraries so that we could use the features of these libraries as well to do simulation. So right now we support Project Q, CQC, and Simulacron. EQSN is one that we worked on ourselves. We tried to make like a really lightweight qubit simulator with the ability to handle the threading really well. Then the QTIP we recently integrated, and it's also open-ended. So if someone wants to put another backend in, we've structured it so that the person who wants to put the backend in just has to implement a few features, a few methods of the backend, and then they should work right out of the box. And then it's just a few lines of code to tell the program to switch the back. So overall, I think the pros and cons of using QuNetSim are as follows. So QuNetSim uses a very high level of functionality. So I would say it's easy for beginners to use if they want to get into quantum networks. It's high level enough that you don't need to spend a month learning about quantum networks ahead of time. You can kind of just dive right in and like figure things out on the fly. Well, it depends a little bit, but yeah. It's good that we can test routing algorithms in the network quite easily, so we don't need to program so much to be able to test routing algorithms. You kind of just set up some sort of routing algorithm, tell QuNetSim to use it, and then it'll work right away. There's lots of logging messages, easy to debug and see step by step what would happen if I were to implement such a protocol in a real quantum network. So I can see piece by piece what's happening at every step of the way. It's easy to debug. It's easy to get started with installation. It's just, we have a pip program, a PyPy project. You just install with pip, and then we've integrated a templating script so we can quickly generate a sample program. And we're actively developing it. So whenever a feature request comes in, I'm there. Then within like hours, I'm seeing this feature, just thinking about how to integrate such a thing. And plus others, we have. We're also starting to get external collaborators. I think we have now 3 features that were implemented by non-original members, which is pretty nice. And the downside, I think, of QuNetSim is that it's slightly simplistic. We don't use so much noise in the network. So, I mean, we're slowly starting to build in QuNetSim these physical models of fiber optic cables, decoherence in the qubits with time and things like this. But this is kind of challenging with like a real-time simulator like QuNetSim is. Real time is not so great because, I mean, it relies on the hardware of the computer. So it's not so easy to do things on the nanosecond level when time is, when things are running at second intervals and stuff like this. So in the second scale, you can't really. So we're trying to think about this, how to integrate physical realism in QuNetSim. For large scale simulation, it's also kind of caps out. I think we get, I don't know, 20 nodes in the network and like qubits that are entangled with 14 other qubits. And then things kind of start to slow down. So if you want to do like large scale simulations, not the greatest choice. And it also has this assumption that quantum internet will be based on packets, like a packet-based quantum internet. So this is not guaranteed yet. There's still kind of talks of how do we build a quantum internet, quantum networks. And it's not clear yet if it will be packet-based or not. So it's kind of a risk that one has to take on using QuNetSim is if they want the protocols to work in the future, they have to also assume that the future internets will be packet-based. Yeah, and I think the people who should use QuNetSim then are beginners. As I said, it's kind of an educational tool because it's high level and it's easy to get started, easy to program with. Instructors should use it as well. So for example, in this semester, we taught, or actually in 2 semesters so far, we've taught a quantum networking course, and we use QuNetSim often for the homework assignments. So we ask the students to write protocols like common protocols like super dense coding and quantum key distribution and things like this. And we ask them to program these things in QuNetSim. And based on the surveys that we asked them, they find it quite helpful, and it really helps them to understand the protocols better. And researchers, I think, should use QuNetSim as well to start testing just the kind of high level protocols. So we see often protocols in the noiseless setting, and this is perfect for QuNetSim because we say let's say we have a perfect quantum network in 50 years from now or 20 years, then what do we do with it? And then if we assume the quantum networks are perfect, then QuNetSim could simulate such a thing. And recently, actually, there was a citation. I think, if I understood the work correctly, it used QuNetSim to test some kind of protocol, which is kind of nice. So we're seeing kind of all 3 aspects of this being hit. And I wrote these things a while ago, and now finally we're seeing it come to life. So I would like to show some example code from QuNetSim. So first, I'll just show the structure of QuNetSim, and then I'll try to do a live demo as well to see how it goes if I have enough time. I think we're only about 20 minutes in, so it should be okay. So what one does when writing a QuNetSim program is first we generally define 2 protocols, one for the sender, one for the receiver. Of course, there could be multiple parties, but this is the most basic case. So in this protocol, we want to send a qubit that's in the excited state or in the 1 state. So the sender will generate a qubit, then excite the qubit, then send it via teleportation. So you see, I don't do anything like generating EPR pairs because QuNetSim will handle this. So it's like just send teleport to this receiver with that qubit, and then don't wait for an acknowledgement that the receiver got this qubit, just keep going. So this is like non-blocking, so to say. And then on the receiver side, the receiver is listening for the qubit, and they're waiting for some time, 10 seconds, and they're expecting it to come from the sender. And then when the qubit arrives, then the receiver measures it and prints the statement. Okay, so this is kind of like the first step, writing the protocols. Second step is defining the network topology. So in QuNetSim, we have these host objects like we talked about. And okay, I didn't label these so greatly, but this is Alice, Bob, and Eve. So Alice is a host, Bob is a host, Eve is a host. Alice connects to Bob, Bob connects to Eve and Alice, and then Eve only connects to Bob. So in this example, Alice is not directly connected to Eve, but she's still able to teleport to Eve. So in the last step, then we launch the protocols. The protocols run in threads, and Alice will run her protocol, which is the sender protocol, which we defined in the first step, with Eve, and Eve will run the receiver side with Alice. And then we just wait for the programs to finish, and then we can kill the software. And then, yeah. So this is what the output would look like. So I run it with Python. So as Alice, Bob, and Eve are started processing. Alice teleports to Eve. They don't share any EPR pairs, so one is being generated. So Alice is sending her EPR pairs, waiting for the EPR to be established. Then we see expected, yeah, okay. And then we see Eve receives the qubit and measures it in the excited state as we programmed it to do. And then the program stops. So like some of the built-in features that we have right now are like sending teleports, and super dense, and EPR, send GHZ. And of course you can send qubits as they are, and one could generate their own protocols. So we have a lot of documentation over here, and the code is all open source. So one could read it and contribute if they wanted to. So let me try to do a quick live demo just to prove that it really works. Let's try to share this here. Okay, you can see the new screen now, I guess. So generally how I start is I create a virtual environment. I've done this already.
You can't see the screen, I don't think.
Oh,
which?
Sorry. Oh, sorry, I didn't click.
More example screen?
Yeah, yes. It should be this one.
Okay, yeah.
Do you see the code? It should be a terminal.
Yeah, code.
Okay, yeah, okay. So now I generally, as I said, start with a virtual environment. I just made it already just to save some time. Activate. Okay, so I can do pip install QuNetSim. So I've already installed it, so it's just going to go really fast. And then what QuNetSim comes with is a template script. So I run this and I just make something, I don't know, sample. And then ask how many nodes in the network, let's say 3. So now I have a Python file. And now I will just quickly open this. Okay. And 1 minute. So you can see the code. Is it too small? I'll make it a bit bigger. So what this generates is this file here. So now I have a template. I have 3 nodes, 3 hosts, and they're all connected, and they're running just a quick protocol where the sender is sending 5 qubits to the receiver after applying a Hadamard gate. And then the receiver measures it. So right away I can run such a thing. So Python sample.py. Hopefully this runs. So you see it's running, and this, I turned off the log messages so you don't get as much detail, but this is running. So one could now modify this program. So let me just quickly. Yeah, so I would want to say something like, if I want to add an eavesdropper, for example, then I could do something like define eavesdropper. And I have, sorry, let me just bring up, I don't have it memorized, but it's, sorry, I accidentally closed my window. Yeah, so there should be able to do receiver, sender, and qubit. Sorry, I don't want to make any mistakes here. Let me just open it up. All right, forget it. So basically what I'd have is a function here that looks like this. I would do something like qubit.measure, and then I would want to not destroy the qubit, so I have something like non-destructive equals true. And now what happens is I program host C to do something like sniff quantum. I forget the syntax exactly, but it's pretty much like this, true. So what this does is it tells host C to listen in on any quantum transmission going through the host. Actually, I'd probably want, in this case, I would want B because B is in the middle, right? And then I say host B sniff quantum function equal eavesdropper. And there's an example of this exactly on online. And it's basically like this. And then when I run this again, the host will, this B will measure the qubit in process. And then if I was more prepared, you would see this host will measure the qubit, this host will receive the qubit, and they'll measure the same thing. And if I didn't turn this on, then the qubit would be destroyed in the process. And it's kind of, so there's a lot of flexibility. One could program all kinds of protocols. Okay, I'm gonna go back to my slides. Okay, should see my slides again. So in the future of QuNetSim, what I think would be interesting is to develop a quantum network simulation open source community, for example, like there is in the classical setting. So in NS3, there's like maybe hundreds of contributors to the project 3 versions already. I mean, tons of contributions. And MiniNet as well, another open source classical network simulation platform with big communities around them. I think that would be really cool to have also in the quantum setting. I think having a graphical interface for building the network would be really nice. It might simplify, especially for beginners, how to construct a network. Might let people skip the step of understanding how to write network topologies using QuNetSim. Again, like improving the realism and the performance. And then the next part is like building quantum network based applications on top of QuNetSim. So what I mean by that is applications that need quantum networks but aren't just protocols, for example. So one such example would be something like, imagine I can write these protocols and then run them on physical hardware directly. So kind of translating Python code to machine code. And actually, this is something we're working on right now. What we want to do is write Python code, run it through a microcontroller to control 2 connected Raspberry Pis, for example. So what the aim for this is to then replace the Raspberry Pis with physical hardware so that we can control physical hardware using Python. I think this would simplify work in the lab tremendously if it was possible to make it work really well. Yeah, and on top of this, generating simulations based on optics experiments parameters. So kind of, if I have my optics lab and I plug in the parameters of my optics lab into QuNetSim, then generating the network topology and generating the simulation code on top of it. And then maybe this way I have an easier time kind of like programming my optics table by doing it in simulation. And then like, okay, I see it works in simulation. Now I can go back to the optics table, configure it better, and then get the output of my experiment. And then the next one is distributed quantum simulation. And this one I want to go into more depth a little bit because we're working on this project as well. So we are working on a project called Interlink, and Interlink is just kind of starting out, and is again a project of Unitary Fund. So what Interlink is a distributed quantum computing simulation platform. So what distributed quantum computing is it's the connecting or interlinking of smaller quantum computers together, because like one could expect that having a small scale quantum computer is easier to control than having a really large one. So one could imagine then connecting small scale quantum computers together to form one single large scale computer called distributed quantum computing. And to do this, you need to network these quantum computers. And some of the challenges of doing such a thing are compiling circuits for distributed quantum computers and also controlling the hardware. So it becomes much more challenging when you have to write communication protocols for these distributed quantum computers and then controlling them precisely and measuring and doing all the entanglement generation and the classical communication. So we're working on kind of a framework on top of QuNetSim that can allow researchers to test their different control algorithms and control methods, and also like their distributed quantum circuit compilation schemes. So yeah, exactly. So Interlink is trying to assist in the research phase for distributed quantum computing, and it's based off of a paper that was recently published over here. You can find the DOI. And this project is something I use as a mentorship project in the Quantum Open Source Foundation. So every 3 or 4 months or so is a program where students around the world can apply and be mentored by someone working in quantum so that they can work on a project related to quantum. And this program is really nice because it's not like anyone can apply, anyone can try, and it's really nice that people volunteer to mentor these students. So I mentor in this organization, and the mentee for this iteration, Rhea Parek, she worked on a lot of this project and got it working really well. So yeah, I mean, the way this program works is you have a single client. So one can imagine I have my computer and my laptop, and I program some quantum circuits, and I expect, I don't know what the quantum computer topology is just I have access to 10 qubits, let's say. Then I input this circuit into my program, which is actually the controller of the network. This controller will then apply the distribution scheme, like the compilation for distributed quantum computers, split the circuit up according to the distributed quantum computer. Then it generates a control schedule. So when does each operation need to execute and which time? And then sends the information to the network of distributed quantum computers. Then this whole simulation happens. Then they reconvene and send the information back. And then the information comes back to the laptop and says, okay, this was your result of the circuit. And the goal is that the client doesn't know anything that happens past the stage of generating the quantum circuit for a single quantum computer. So this is what we're trying to work on right now and make this really efficient and easy to do for people who are interested in this topic. Yeah, so that's everything I want to talk about. And yeah, thanks for listening. And I see some chat activity, so hopefully there's some questions.
Yeah, thank you, Stephen. That was fantastic and very interesting. Let me just quickly say, I know many of you had to join late because the Meetup site was down. That's okay. So as always, I've been recording this and I'll post it as soon as it's available. So you won't have missed anything. Yes, there were many questions, and I guess we can just go in order here. When you talk about quantum simulator, does it include neural networks and optimization in training hybrid networks as well?
No, nothing to do with that. But I mean, I think people are talking about this topic. I can't say anything. I don't know anything about that. I'm sorry.
That's all right. What kind of protocol do you use? Do you have any examples? Maybe you answered that later in your talk.
Yeah, so I mean, you could check out the GitHub page. There's I think we have 10, 15, but around 15 examples there, ranging in complexity. Also in the Git repo, there's examples that aren't so well documented, but you can read the code and there's quite a few examples there.
Good, and yeah, people are asking for the GitHub repo. So there it is right now on the screen. You said it's transmitted through threads earlier. Do you mean threads as in the computer science terminology of it? Meaning it could be multi-threaded as a functionality, or do you mean different kind of thread?
Yeah, no, just normal threads. And threads in Python. So we're using the multi-threading library quite heavily so that the nodes are running independent of each other. There's no, like, synchronization is up to the user. Yeah.
So I have several questions. One of possible quantum network application is position verification. Is this possible to simulate too? Some time delay in correspondence to distance. What other designs apart from the packet quantum internet are considered? Are there some advanced modules as nodes with MDIQ KD protocol available? Or I need to implement all alone?
Okay, so, I mean,
that was many questions.
Okay,
many questions, yeah.
So I'm like, maybe I'm a bit sleepy by now. Let's start with the first, the top one. What the first one was? This is from Mikael. I have several questions.
Right,
This one, okay. Yeah. Position verification. Supposed to simulate too sometimes. Actually, I don't know about this protocol, but time delay is something that can be done. So, for example, we want to write some protocol that's sending qubits, but the qubits mean something different. Like either it's an EPR pair or it's a qubit encoded with classical information. And to distinguish this, for example, we use like time multiplexing, so to say, put that in air quotes. But what that means is we use a time delay to distinguish. So let's say the time between transmissions was 1 second, that means it was an EPR pair. The time delay between transmission was 2 seconds, that means it's a qubit that needs to be measured. So something like that. So time delay is something we use QuNetSim for. And because it's real time, it's easy to do. You just do like time.sleep and then you can simulate such a thing. Other designs, apart from the packet-based internet, is it's kind of complicated. I guess that they're kind of working on such a thing, but basically no header information on the qubits. So I'm not sure how that would work exactly. I think this is still in progress. I think having no packets, having, for example, not a packet before, not packetizing the quantum information, but having maybe classical information ahead of time and then comes the quantum information. So this is not really packet-based because it doesn't arrive together. It might be as like a classical pre-message, then quantum like post-message or something. So this is some other designs like this, but I think it's I don't know. In my opinion, would be extremely hard to just have pure quantum internet. Well, I mean, one could imagine also that you use the qubits themselves as the header information. So maybe you encode qubits classically. Let's say you put like excited state, ground state, excited state, and this represents kind of like the header information. You can kind of see where the frame is like that. But yeah, I think this is still an open problem, and this is something that will be open for a little while too, until the technology catches up. And then are there advanced modules as nodes with MDI QKD protocol? This I would say no. You'd have to implement them on your own. I mean, we have a sample of just pure QKD in the list of examples in the repository, but advanced QKD things like this we don't have. Okay.
Good. And I think the last question with regards to QoSF, do you have many projects? I'm looking for one, please, to be mentored.
At the moment, I'm going to have one more project. I'm thinking about if I should make two, but I'm not sure how much. I mean, it is a bit time consuming as well. It's a voluntary effort, and last semester was quite well, but I'm thinking at least one for sure, and then maybe two, but not many. Let's say. And
will slides be available? Or
yeah, I can send them, no problem.
Okay. I'll post the link to that also then. Super. So thank you again, Stephen. That was fantastic, and thank you all for joining. And I'll post the recording as soon as it's available.
Yeah, thanks a lot.
Thank you, everyone.
Thanks. Thank you.
See you. Thanks.